Hello everyone. Let's begin today's session with a thought. Have you ever used a jack to lift a car or watched workers use pulleys to raise heavy loads at a construction site? These simple machines make our work easier. But how do we measure how good a machine really is? Is it only about how much it reduces the effort or also about how efficiently it works? That's where three important quantities come together: mechanical advantage, velocity ratio, and efficiency. Each tells us a different story about the machine, and together they give us a complete picture of its performance. By the end of this lesson, you'll see exactly how they are related. Let's start with mechanical advantage. It is defined as the ratio of load to effort. In words, the formula is mechanical advantage equals load divided by effort. For example, if a machine helps us lift a load of 200 newtons by applying only 50 newtons of effort, then mechanical advantage equals 200 divided by 50, which gives 4. This means the machine multiplies our effort 4 times. The higher the mechanical advantage, the less effort we need for the same load. That is why levers and pulleys are so useful in daily life. Now let's look at velocity ratio. Velocity ratio is defined as the ratio of distance moved by effort to distance moved by load. In words, the formula is velocity ratio equals distance moved by effort divided by distance moved by load. For instance, if in a pulley system the effort moves to meters while the load rises only half a meter, then velocity ratio equals to divided by 0.5, which is 4. Notice something interesting. Velocity ratio depends only on the geometry of the machine. It is not affected by friction or other energy losses. A higher velocity ratio means the effort moves a greater distance to make the load move a smaller distance. Now let us define efficiency. Efficiency tells us how effectively a machine converts the input work into useful output work. It is given by the ratio of work output to work input multiplied by 100%. In words, the formula is efficiency equals work output divided by work input multiplied by 100%. Here, work output equals load multiplied by distance moved by the load. Work input equals effort multiplied by distance moved by the effort. Substituting these values, we get efficiency equals mechanical advantage divided by velocity ratio multiplied by 100%. This shows us that efficiency connects mechanical advantage and velocity ratio into one unified relationship. Let's carefully derive this result. Step 1. Work output is equal to load multiplied by distance moved by the load. Step 2. Work input is equal to effort multiplied by distance moved by the effort. Step 3. Efficiency is equal to work output divided by work input. Substituting, this becomes load multiplied by distance moved by the load divided by effort multiplied by distance moved by the effort. Step 4. Rearranging, we get load divided by effort divided by distance moved by effort over distance moved by load. Step 5. But load divided by effort is mechanical advantage and distance moved by effort divided by distance moved by load is velocity ratio. So we finally get efficiency equals mechanical advantage divided by velocity ratio multiplied by 100%. This is the exact relationship we were searching for.
Let's work through an example. A machine lifts a load of 300 newtons through a vertical distance of 0.25 meters. The effort moves 1.50 meters and the applied effort is 80 newtons. We need to find the mechanical advantage and the velocity ratio, then calculate the efficiency, and finally determine the effort that would be required if the machine were ideal. First, the velocity ratio is the effort distance divided by the load distance. That is 1.50 divided by 0.25, which equals 6. Next, the mechanical advantage is the load divided by the effort. This is 300 divided by 80, giving 3.75. For the efficiency, we divide the mechanical advantage by the velocity ratio and multiply by 100%. That's 3.75 divided by 6 multiplied by 100, giving 62.5%.
Finally, in an ideal machine, the mechanical advantage equals the velocity ratio, which is 6 in this case. The ideal effort would then be the load divided by the mechanical advantage, or 300 divided by 6, which equals 50 newtons. Let's wrap up. A machine can't create energy, it only channels it. In symbols we kept repeating, W in equals E times D sub E, W out equals L times D sub L, and ideally W in equals W out. That leads to M A equals L over E. We are equals D sub E over D sub L, and the efficiency relation eta equals open bracket MA divided by we are close bracket times 100%, with MA equals we are only in the frictionless ideal. From levers and pulley blocks to gears and jacks, engineers tune geometry to get the force distance trade-off they need, then fight losses with good materials, lubrication, and design. I hope the energy picture behind machines now feels intuitive. When force goes up, distance usually pays the price. See you in the next session, where we'll apply these ideas to specific machine types and sharpen your problem solving even more.